Hi there and welcome. We're going to take a look at a circuit called an RC circuit. Now the R stands for resistance and the C stands for capacitance. So this is a circuit that has both a resistor and a capacitor in it. In its simplest form, like you see over here, they're in series with one another in a battery. Now I think you guys recognize that if we were to only have the capacitor in the circuit and we connected the battery up to it, charge would flow from the battery onto the capacitor plates. The purpose of the resistor is to slow down this flow, and that's basically all it does. So instead of the charge showing up on those plates nearly instantaneously, it can take a while depending on how much resistance you have and how big the capacitance is. So a big capacitor might take longer to fill, which makes sense, and more resistance is going to slow down the current more. There is what we call a time characteristic of this circuit, which we represent with the Greek letter tau. It is basically a measure of, this is going to sound really strange, but how long it takes for 63% of the charge to flow onto the capacitor. Why the 63%? It's a mathematical thing, which I can kind of explain in a minute. And what it's equal to is the product of the resistance and the capacitance. And it does have the unit of seconds. So probably didn't know this, but if you multiply ohms by farads, you get seconds. Really weird, but there it is. Where this gets used is in a function. There's a function that is the amount of charge that will be located on the capacitor at a given amount of time, and it is a function of the total charge, big Q, and this very strange looking thing in the parentheses, which was 1 minus e to the negative t over tau. Why this crazy thing? Well, it requires calculus actually to explain where this comes from, so we're not going to do that. But what we can do is look and see how this thing performs as you go from a time of 0 to, say, a time of infinity. You would imagine if you let it go infinitely long, all the charge that would wind up on the capacitor will wind up there. And that total charge is still going to be calculated using our trusty old capacitor formula, which depends on the capacitance of the capacitor and the voltage that's applied. To get to that maximum Q, we're going to start out at time equals 0. Now, if I plug a 0 into the t up here, you wind up with e to the 0, which anything to the 0 is a 1. So I wind up with a 1 minus 1, which is 0, times Q. So when I first start out, I'm going to have no charge on the capacitor plate. That kind of makes sense to me, hopefully to you too. Now, as the time approaches a number like really big number, like infinity, we're going to wind up with infinity. Infinity over any number is just infinity. But the negative exponent is the interesting part, because the negative exponent means that we are going to take 1 over e to the infinity. Now, 1 over infinity is 0. So basically, this function goes from being 1 to 0. So 1 minus 1, like we said at the beginning, is 0, but 1 minus 0 is 1, and 1 times Q is Q. Just so you understand, it's not going to take infinitely long to reach maximum value. I mean, it's one of those weird parts of math where it takes an infinite amount of time to get there, but in a practical sense, it gets there rather quickly. As a matter of fact, like I said, when you reach the point where you've reached 1 tau, you've already at 63%, and you keep going up to a few more tau, you're going to be nearly at full capacity. I'd like to do a practical example of this problem. A typical problem might be something where you have a resistance of, let's get a big number in here, 100,000 ohms, which is pretty realistic, and a capacitance of, let's say, 5 times 10 to the negative 6 farads, or a microfarad, 5 microfarads. We'll make the voltage 10 volts, and we will make the time that we're seeking here is going to be, let's try 3 seconds. First thing you want to do is find out what tau is. And tau is going to be R times C. So that's going to be 100,000 ohms times 5 times 10 to the negative 6 farads. This is going to come out to 5 seconds. What that means is if I run this circuit, after 5 seconds, I'll be 63% of the way to full. The next thing we want to do is figure out how much total charge we have, and that's Q equals C times V. The capacitance again, 5 times 10 to the negative 6 farads, and the voltage is 10 volts, which is going to give us a total charge of 5 times 10 to the negative 5 coulombs, or 50 microcoulombs, however you like to put it. Now, using our function formula, the amount of charge we're going to have, let's plug all this stuff in. We've got a total charge of 5 times 10 to the negative 5 coulombs, and then we're going to have 1 minus E to the negative 3 over 5, and at this point you would have to use your calculator to figure out what our charge is at that moment. And let's do that. So the answer I got was 2.26 times 10 to the negative 5 coulombs. Now it's worth noting that you can play around with this function to get a second function that would tell you how much time it would take for a capacitor that's at full charge to lose all its charge. So you can set up a circuit where, say for instance, you're using an RC portion of the circuit to slow down the rate at which a capacitor discharges. So let's say for instance you've got an LED in your circuit and you want, when you turn the power button off on this device, that it slowly dims away. Well, all you have to do is take that function and get rid of the portion, the 1 minus portion. To me, this makes sense because this function here, e to the negative t over tau, is something that goes from 1 to 0 over time. And so when you discharge the capacitor, it'll start off at full charge, where this is multiplied by 1, and gradually, as this number shrinks down to 0, go to 0. You can use it that way as well. All right, well, I hope this makes sense to you, and I hope you do well on your worksheet, and good luck.